Okay. Hello. Can you guys hear me? Can you guys hear me? Hello. Can you guys hear me? All right. So let's give it one more minute while we're receiving more attendance. Okay. Today is the first lecture of our new session, so we always have some students coming late, so on and so forth. Let's give it one more minute while we're receiving more attendance. Okay. And also at the same time, can you do me a favor by changing your names, your display name into your registered name? Because I have a list right in front of me. I just want to make sure the students they're arriving on time. If you use just like alpha, beta, or like a J something, I won't be able to recognize you. Okay, can you please do me a favor? Change your display name into your official registered name. So I will be able to do the mapping. All right. Especially, I think we have a student here. Your name is Jay. So can you convert it into your real name? So I'll be able to see you. All right. So maybe one more minute while we're receiving more attendance. Okay, it's 9:02, so let's get started. Okay, guys, welcome to our North American Math Competition courses. So before we started, just want to have a very short and brief introduction about our course, because we have a lot of new students that just arrived. So our course is actually based on different sessions. We have 8 sessions in total. So each session we're trying to dedicate to a specific topic in math competition. So previously we have already talked about our counting and probability. We talk about the number theory. We talk about the 2D geometries, the coordinate geometries. And from this session, we're going to be talking about more on the algebra. You know, algebra is actually a very important step for the entire math competition. And especially for our students, algebra should be the first thing you learn from pretty much your elementary school, right? You learn how to do the numbers, how to do the basic calculations, so on and so forth. And one of the very, very important topic in the entire algebra is actually function. You know, talking about a function, I think you guys, we shouldn't be very unfamiliar about function. Function is actually a concept which we learn from day one, and we have a lot of day-to-day interactions with our life. Just want to give you guys a very good example. Let's say, let me jump to our lecture. Let's say function. What is function trying to say? Function just trying to find out a relationship between two variables, right? This is pretty much a course, a very rough understanding for function. Function means a relationship between different numbers. Just want to give you guys a very easy example in our everyday life. Let's say sometimes you go to a website or something, you have a 20% off, for instance, right? This is actually, you can see from time to time. So what does 20% off mean? It means the original price is going to have a deduction about 20%. Let's say you have the original price, right? You have the discounted price, right? Let's say, I don't know, maybe this $10, right? After the discount, you go to $8. $100 after the discount, it goes to $80, right? So I think this is actually a picture or like a situation we're very familiar with from day one. You know what? This is actually a function because this is kind of a relationship between two numbers. The first set of number is kind of the original price, right? And the second set of number we call the discounted price. And what's the relationship changing from the original price all the way to the discounted price? We use a 20% off, right? I think this is actually a very, very basic, a very understandable concept that we have in our everyday life. And that is actually a function. Later, I'm going to show you guys the definition for function, but I just want to, at the very beginning, try to say that function is actually a concept, in our everyday life. We're actually using function pretty much in a day-to-day basis. Another example is, let's say you want to know the temperature for each day, right? So let's say this is your January the 1st, all the way to December the 31st, right? This is like you have 365 days. And I just want to know, maybe January the 1st, what is the rough temperature? January is cold, right? January, let's say 0 degree, right? All the way you go to June the 30th or something like just today, right? Today is pretty hot, right? 30 degrees. And all the way you go to December, the temperature will drop back again, goes to, I don't know, 10 degrees, something like that. So you're kind of having a mapping or kind of a relationship, okay, at a certain date, the temperature is expecting in a certain range, right? This number can from 0 all the way to 30, and from 30 all the way you draw back to 0. This is also quite understandable in our everyday life. And this is also a function because it's kind of a relationship between the one numbers or one set of numbers to the other set of numbers. Right? So we can name a few, right? We can have like so many examples in our everyday life. So that being said, our life is actually interacted with the function, the concept of functions all the time. So everything we're going to be talking about in our current session, the entire function, is going to be very applicable to our everyday life. So this is a concept we should be very familiar with, right? And actually, not only for our everyday life, for the entire mathematics, function is actually a very important concept. Or we can just say function is a foundation for the entire algebra. A lot of concepts, a lot of interesting properties, they can be elaborated from the function. So that's the reason why we like to choose an entire session, 10 lectures talking about the functions concept, because function is like so close to our everyday life and it has the interactions from day to day. All right, so this is kind of like an introduction why we like to talk about function. And function is not a concept that's too far away from us. This is actually in our everyday life. All right. So before we get started, I want to have a very quick overview or kind of like a review what's going to happen in our current session, right? This is like a preview. So what we need to talk about in this functions umbrella. So we're going to get started with the basic function definition concepts. So we say the function basics. This is pretty much for today's lecture. I think you guys should be very familiar with, but I still want to take this opportunity to summarize all the concepts together and give you guys a little bit, some interesting property here, some interesting property there, and give you guys some real problems. So therefore, you'll be trying to do a mapping between the concepts and also the strategies, how to solve the problem. So we're going to start our lecture talking about the function basics. And then later, we're going to go to the function properties. As long as you learn a new concept, right? You want to know the definition, you want to know some basics. The next step, we're going to learn the properties, right? We need to know for a specific concept, what kind of flowery properties, interesting properties, and potential these properties can basically help us solve some other problems in the future. So later, we're going to spend some time talking about the functions property. So these function property are actually the generic property for all the functions. We're not specifying to one type of function, a linear function, a quadratic function, a trigonometry function. No, we're talking about something pretty overall, all the concepts, all those properties for the functions. You know what? For instance, like this is an increasing function, this is a decreasing function. We call it monotonicity. No problem. Later, we'll give you guys more explanation in the future lectures. But here, just give you a quick preview. We're going to talk about some even functions, some odd functions. Function has some symmetric property, and even odd is actually a very important one to differentiate different functions. We're going to talk about the periodicity of a function. Some functions, after a certain amount of time, they will repeat for themselves. We call this is actually a period. So these are considered to be the basic properties of a function, and they're not specifying any type of function. All the functions, they will have such a property. So this is what we are going to talk about in our future lectures. And then we're going to talk about the graph of a function. There are many ways to denote a function. Later, we're going to actually give you guys all those information. And one of the most powerful way, and one kind of the preferred way, is actually using the graph. The graph of function can actually tell a lot of interesting properties of a function. And also, we can utilize that graph of the function, try to solve a lot of problems. So we're going to spend the lecture talking about different types of graph for function and how to make the connections between the graph and all those interesting properties. Okay, we're going to talk about later. And then moving forward, we're going to talk about two very important types of function. One is the exponent function. The other one is logarithm function. So these two parts are considered to be the advanced function. And if you guys are familiar with some of the math competition, you might see these two concepts from time to time. What is the logarithm? What is the exponents? And what are the relationship between these two functions? So these two functions can actually consider to be a twin brother. A lot of properties from one can be transferred into the other one. So we're going to spend some time, give you guys some basic introduction about these two functions and what are the flowery properties, so on and so forth. Okay. Number 5, we're going to talk about the rational function and fraction function. The rational function and fraction function, you guys already learned that in your day school for sure, but maybe due to whatever reason, the teacher does not really give you the kind of like a summary to see what's the relationship between these two function types and what are the interesting properties between these two function types. And actually, these two guys will be tested every single year in our American and Canadian math competitions. All right, so we're going to spend some time talking about the basic properties and some important applications of these two types of functions. And number 6, we're going to give you guys a very specific type of function we call a Gauss function. Gauss function is kind of like, what should I say? It's a favorite for the American and Canadian math competition. These are not a very typical function you learned that from your day school, but they will be tested in the math competition from time to time. So that being said, we need to spend some time talking about the Gauss function. Okay, later we're going to give you guys a lot of examples of how to utilize the Gauss function to solve some real problems, and that will be one of the important part in our current session. And number 7, we're going to talk about some max value and minimum value. As long as I give you a function, sometimes these functions can have a maximum value and a minimum value. So how to determine the maximum value and minimum value, how to use different technologies, try to classify them into different categories. This is also a very important part. If you do a quick review, you try to recall some of the real math competition exams, sometimes they really ask you to say, what is the maximum or minimum value for given function in a given interval? Right? So this is actually also a very important topic we'd like to share with you guys. And the last but not least, we're going to talk about a Diophantine equation or Diophantine function. So what is a Diophantine function? Diophantine function is a special type of function, which you have more variables than the equations. I'll give an example. Normally speaking, if I give you x plus y equals to 1, 3x minus y equals to 3, okay? Just give an example. This is a system equations, right? Because you have two equations, you have two variables, of course, you will be able to solve this equation, figure out the value, what is x, what is y, right? This is quite understandable, and we actually learned that for a long time. However, sometimes I give you a function like this. I don't know, 3x squared minus y squared equals to 4. That's it. I only give you one equation. However, this one equation contains two variables. Everyone knows that this equation should have infinitely many solutions, right? Because two variables with one equation, you can have whatever whatever number of solutions you like. You're correct. So if we talk about the solution for such an equation, this might not be so useful, right? Because we spend a lot of time talking about the equation which has infinite many solutions. It doesn't make sense too much. However, if I want to shrink or constrain the condition a little bit, instead of giving me all the solutions, which are infinitely many, can you find out the positive integer solutions for such an equation? Positive integer solutions means x, y, they must be positive integers. So that being said, maybe you won't be able to have too many solutions. Maybe you only have a limited type of solutions, right? So maybe if this solution, let's say I'm going to give this, if this is plus 3x squared plus y squared equals to 40. Okay, I think this one makes more sense. So you see, two perfect square numbers, adding them together equals to 40, and you want to make sure both of them are positive integers. So intuitively, there are not so many candidates for x and y. Is that right? If we are on the same page, this is actually a very important part. We like to say in our future lectures, such an equation or such a function, you have more variables than the function itself. We give them a name. That is actually a Diophantine equation. This is kind of the name of the equation, Diophantine equation. And Diophantine's positive integer solution is actually a very interesting part for the entire math, not only for math competition, but overall for the entire math. This is kind of a very hot spot, a very hot topic for all those kind of math studies. A lot of mathematicians actually spend their kind of like entire career life trying to find out what are the standard or generalized solution for such a Diophantine equation. Of course, in our lecture, we won't be able to give the same complexity as the mathematicians trying to investigate. But of course, from our view, we still want to give you guys a little bit summary and try to see how can we find out a solution for these type of equations or this type of functions, because they are very important. And if you check the American and Canadian math competitions, they will test it from time to time. All right, so this is a very quick and short preview of what we will be talking about for our entire session. Okay, so you have any questions for me? All good? Yeah, bear in mind, I'm actually monitoring the group chat all the time. So as long as you have any questions, you can post your answer into the group chat and I'll be able to provide you the answer in a real-time basis. Okay, and at the same time, which I preferred, instead of typing, you can just basically unmute yourself. You can raise your hand and you can just basically ask me the question. So everyone can hear your answer and we can just give you the feedback right away, right? This is a very dynamic lecture. So I hope you guys can, participate as much as possible. You can turn on your camera if you like, but there's not really compulsory. Sometimes if you turn on your camera, you can see each other. There's kind of also a reinforcement for your study. It's up to you. Okay. Okay, if all good, that's pretty much an overview. So let's jump to the first part of our session, function basics. Okay, this is actually our first lecture. Function basics. Okay, so talking about function. So the definition of a function, I think at the very beginning, we already know there's so many examples. We give you guys, 20% off, or, like the temperature to the date. So these are the basic, very, what should I say, very understandable concepts, right? Very understandable examples for the functions. So moving forward, if you want to have some real definition for a function, so how can we define a function? So the definition of a function can actually go for 2 steps. Let's go for step number 1. Step number 1 is more like a basic understanding using our human beings word. We can actually define a function. So what is the step 1's definition? Function is the idealization of how a varying quantity depends on another quantity. Right? I think this is quite intuitive, quite understandable definition. Function can be defined or can be idealized. Try to see the word, okay? Idealized, how a varying quantity depends on another varying quantity. Why do I use the word idealized? Because sometimes we do not have the function first. We have the, like this is 2 varying quantity first. Let's say I have a quantity A, I have a quantity B, right? I find out 1 is always go to, I don't know, 2, 2, 4, 4, 8, 8, 16. So we have these numbers first, right? After seeing all those numbers, we like to idealize them, or we want to abstract them. So we find something, maybe a number from A times 2 goes to B, right? So most of the time, we do not have a function first. We have all the numbers, we have the quantity first. And then after observing all those quantities, okay, let's try to generalize them into different, into more abstract way, which is a function. Right? I think this is kind of very understandable concepts, right? So this is actually the step 1 definition for function. Okay, like I said, step 1 definition is more like human being using the word, but from the mathematician's perspective, they don't like all those human beings words. They like to have some pure mathematical way to give the definition. So let's try to see the step 2. Step 2 way how to define a function. In order to define the step 2 definition, we need to introduce some concepts. I'd like to ask you guys, set and map. Okay, so before we get started, let me ask you a question. Are you familiar with the set concept? So I want everyone to give me some feedback because our lectures are always adapted based on your understanding. Okay, can I have some quick feedback? You can privately chat with me. You can public if you feel shy, but I don't think so, right? This is not really, this is not something so, I mean, you don't really have to get shy, right? So any problem, any question, just let me know. All right. Yeah, I think most of the students, they have some, you see, I'm actually watching the group chat. Most of the students have some basic understanding for the set. So let's do a very quick review about the set, because set is actually a foundation concepts we like to talk about for our entire mathematics. Let's take this opportunity to do a quick review. What is a set? So what is a set? The set, you can take it as a collection. The set can be kind of considered as a collection. So what does it mean? You're trying to put all things. Okay, here I use a more human being words, things. Later, I'm going to give you a more professional definition. Okay, we put all things which have the similar property together, this will create a set. So what is a set? Set is considered to be a collection. So what a kind of collection? We put all the things which has the similar property together. You're going to create a set. For instance, I just want to give an example. For instance, you can have your pants, yeah, your shirts, right? Maybe your shorts, everything all together. So this is a collection of all your dress, right? This is all your clothes, all your dress. So this is actually kind of a collection. You put all the similar things together. You say, okay, this kind of similar things as a collection, we give a name set. Another example, let's say all my fingers, right? I want to have my thumb, you know, my kind of like, what should I say? My thumb, my index finger, my middle finger, my ring finger, my pinky, right? All together, all the fingers. As long as they come from the similar property, they have the similar property, you will be able to put them together. And this kind of putting them together, we give a name. This is a set. Okay, so as long as you know a set, how can I denote a set? There are actually different ways to denote a set. Denote a set. The most straightforward way is basically listing them out, right? Let's say I have a set 1, 2, 3, 4, 5, whatever. So this is actually you listing them out, right? These are actually considered to be a set. So my set, all the numbers, I put them together, I can say these numbers, what kind of the common properties they have all together? These are the positive integers. Right? This is actually a very primitive way, a very basic way to define a set and to list out all the numbers in a set. Okay, so all the way comes here, I think we already have a very good understanding. What does a set mean? Set means we put all those property, all those elements, all those things together as long as they have a similar property. But these are all kind of like human being language. Do we have a more well-defined, like a better mathematics language? So here's the definition of a set. Using a more mathematical way is a set is a collection of well-defined objects. A set is a collection of well-defined objects. I think most of the word you understand here, right? The most important thing is, what do you mean by well-defined? This is actually a very important thing we need to talk about, talking about a set. So at the very beginning, a set means a collection of all the things, right? Which they have the similar property. But similar property, this is a very vague word, right? So what do you mean by similar property? Actually, from the definition of a set, it says these property must be well defined. It must be very clear without any ambiguity. So at the very beginning, we give an example, right? All the clothes, they can actually be considered as a set because the definition of clothes is very clear, right? Like I said, your shirts, your shorts, your pants, you know, so on and so forth. This is very clear. Fingers, you only have like 5 fingers, right, for your one hand. So basically, you will be able to define. That's very clear. There's no ambiguities, right? So this is no problem a set. This is no problem a set. But what if I give you like this? Beautiful girls. Can we use beautiful girls as kind of a similar property and try to define a set? Can I use the criteria beautiful girls? Okay, let's try to find a collection of all the beautiful girls, and then let's just try to make a set. Actually, the answer is no. Why? Because, like I said, clothes, fingers, these are very clear concepts, right? There won't be too much ambiguities. However, beautiful girls, this is kind of like a very vague concept, right? A girl is beautiful in my eyes might not be the same in your eyes because different guys have different standards. So that being said, beautiful girl, this is not a well-defined concept. This is kind of like, it really depends on different people, different region, different culture, so on and so forth. So that being said, a beautiful girl cannot be a criteria in order to form a set. So this is a no. But can I make it more tangible? If I really want to find some girls or some popular girls, instead of using beautiful girls or even popular girls, right? Popular girls, right? Like I said, popular, how can you define a popular, right? This is not really a well-defined criteria to filter them out. However, if you say this is no, what about this guy? Girls whose Instagram has more than 10 million followers. Okay, if you want to say a popular girl, we're on the same page. Popular, it's kind of difficult for us to define a popular, right? So popular girl cannot be a criteria to create a set. Then what about I say girls whose Instagram has more than 10 million followers? That is going to be a criteria for a set because it is very easy for me to identify what is more than 10 million. That's it. There's no ambiguity. So therefore, girls who has Instagram follower more than 10 million, this is a perfect set. You will be able to define such a set and list out all the elements one by one. But beautiful girl or popular girls, this is not a clear definition. You won't be able to create a set and won't be able to list out all the elements one by one. Okay, so I think this is the first thing I want to say. So well-defined is a number one important property for a set. It must be clear without any ambiguity. Number two, we want to say for set, in a set, all the elements must be unique. In a set, all the elements must be unique. I think this is kind of like a human being's requirement. The human just try to give, okay, this is a specific condition, a specific constraint for a set. For instance, I give a set 1, 2, 3. No problem, this is good because you only have 3 items. So these 3 items are unique. But if I want to give you 1, 1, 2, 3. 1, 1, 2, 3. Then you have 2 elements. They're identical. Okay, according to our criterion number 2, this is not a set. If you want to change this into a set, no problem. You need to remove 1 element. 1, 2, 3. This is a set. Okay, so don't ask me why this is kind of human beings definition. People defined or people require that all the elements in a set must be unique. If you have more than 2 elements that are the same, no problem, remove the identical things. All the remainers, all those kind of remaining ones, they will be a set. So this is the number 2's requirement. They must be unique. Number 3, order of the elements in the set does not matter. When you have a set, 1, 2, 3, and what about 2, 3, 1, or 1, 3, 2? You know what? From a set's perspective, there are basically identical. They're exactly the same thing. As long as you have 3 items, there are 1, 2, 3. I don't really care how they're gonna do a kind of ordering. As long as they're in the set, we're considered to be the same. So this is also human beings definition. So the order does not matter. So this is kind of a comparison with the permutation, right? A permutation, when I have 1, 2, 3 as one permutation and 3 to 1, they are not considered to be the same permutation, right? However, a set is okay, because set is a collection. I have all those 1, 2, 3 items in the kind of like in the bulk, right? I don't really care which one goes first or which one goes later. So as long as you're all within my big umbrella, you're good to go. Okay. So this is actually a basic concept about a set, right? And we have a lot of like concept. We have a lot of like examples in our real life, right? To the set. For instance, I want you to list out all your relatives. Of you, right? So this is actually a clear set, right? So all the relatives, like close relatives, for instance, this is actually a set. All the real number, all those maybe positive integers, right? This is a set, right? 1, 2, 3, 4, up to whatever. So these concepts are actually very familiar, right? Okay. If all good, I think we have some basic understanding about a set. We can go to the second definition of a function. Step 2 definition. So this step 2 definition goes like this. If A and B, they're both 2 non-empty set, then a relationship, you give a name F, from set A to set B is said to be a function. What is that? If you have 2 sets, A or B, right? The one set can be your relatives, and the other set can be your paints, right? That's kind of like things. So if you want to define a relationship from set A to set B, I don't really know. Maybe you have A1, A2, A3, B1, B2, B3, right? You have kind of a relationship. I don't know how this relationship looks like. Maybe I just want to give you like a very easy example. And what about this way, right? This is kind of a relationship, but you can have like different kinds of relationship, right? If you have 2 non-empty sets, if they're empty, nothing inside, I don't think there's too much to say, right? 2 non-empty sets. If there is a relationship F from A to B, okay, you can say this kind of relationship is called a function. Still remember, a function is what? Function means one variable depending on the other variable, right? You have the original price, you have the discount price. So this relationship is actually helping you to know, okay, what is the discount? 20%, 30%, 50%, right? Or how you can get the relationship between A and B, right? So this is actually the second category of definition from a function. It's actually defined on 2 sets, set A, set B, and then there's kind of a relationship from the elements in set A to the elements in set B. They are considered a function. Okay, so all the way comes to here, we need to have a quick think. The question, all the way comes to here, we just talk about a relationship from set A to set B. But we really do not really specify how this relationship looks like. right? We just say there's a relationship between A and B, but how this relationship looks like. So let's do a little bit breakdown. A relationship from A to B. How can I understand? Okay, let me give you some examples. Let's try to say some real examples. Let's say if you have add one relationship, okay? So my relationship name is add one. Okay, I have an A set, I have a B set, right? A can give you 1, 2, 3. Just want to give a quick example. So this is 2, 3, 4. If my relationship is add one means what? 1 go to 2, right? 2 go to 3, 3 go to 4. So this is kind of, as long as you give a number in A, I would be able to find a number in B. So this is more like a one-to-one relationship, right? There's no ambiguity. You give me a number in A, you must find one number in B. You give me a number in A, I must find a number in B. This is a one-to-one relationship. Okay. However, I might have some other stuff. I have a set for A, I have a set for B, right? A and B. So A, maybe I want to say this is a student. Oh, we are students in our classroom, for instance, A1, A2, A3. Okay. The B set, I will say students' parents. Right? You have A's father, A1's father, A1's mother, right? A2's father, A2's mother, A3's father, A3's mother, so on and so forth, right? I just want to list out all their parents. So if we want to find out that this relationship is find parents. Okay, parents, mapping to their parents. What are you going to do? A will be mapped to A1, A2, right? Because you have two parents. B will be mapped, A1 will be mapped to A1, A2, and B will be mapped to B1, B2. Oops, give me 1 sec. It looks like my sharing is frozen there, right? So let me just give me 1 sec. I will stop the sharing and reshare it. Sometimes they have this technical issue. Let's do another reshare and you will be able to see my screen. Yeah, now it's working perfectly. Okay, so what I'm trying to say in the second part is that you can actually find out a relationship. So this relationship, let's say in the A set, is the students, A1, A2, A3. And then we go to the B set. B set are the parents of the student. You know, A1, father, mother, A2, father, mother, A3, father, mother. If my relationship is that, please try to find the parents. So how are you going to find their parents? The parents is actually doing a mapping, right? From A1 to A1 father, A1 mother. From A2, A1, A2 father, A2 mother. From A3, A3 father, A3 mother. Is that right? So in such a case, you can find out one element in the A part will be corresponding to multiple elements in B part. Is that right? So that being said, I want to give a name, one to many. So, right, this is kind of a mapping from one element to many elements. Here, many means two, right? If I also include the grandparents and the relatives, there might be more than two. But generally speaking, you get an idea, right? From one element, you basically map to multiple elements. So we give a name, one to many. Okay, number 3, I want to do something also quite similar. I have an A set, I have a B set. Maybe I can find some characters from the TV series. And the B part is actually the name of my TV series. I'll give you an example. Let's say I have like Walter White, something Jesse Pink, and Jon Snow, Tyrion Lannister. Okay, these are very famous, right? Very familiar leading characters. So I give you maybe 2 TV series. One is the Breaking Bad. The other one is the Game of Thrones, right? Game of the Throne. Okay. So if my mapping is that, please find out which character comes from which TV series. Of course, you know these 2 guys, right? All right, Walter White and Jesse Pink. There comes from the Breaking Bad, and Jon Snow and Tyrion Lannister. They come from the Game of Thrones. This is also understandable, right? We have multiple characters. They come from the same TV series. So that being said, is what? You have actually multiple items mapping to one thing, right? You have 2 characters or even more characters. They come from the same TV series. So that being said, you see this is a many-to-one relationship. A many-to-one relationship. Okay, so this is the reason why we like to do a little bit breakdown. Previously, in the second phase of our definition, we just say a function. A function can be defined as a relationship from one set to the other. That's it. However, if you really break down a little bit, we're going to find out the relationship between 2 sets. They're not so easy. They actually have multiple scenarios. They can be a one-to-one mapping. They can be a one-to-many mapping. They can have a many-to-one mapping, right? And just within all those mappings, are they all considered to be a function, or only a small portion of them can be considered as a function, right? I think the definition does not really give you too much. But after some quick analysis, you can find out, oh, there are so many scenarios, and you need to figure out which scenarios can consider as a function, which scenario cannot be considered as a function, right? This is not really given by the definition, and we need to actually give some clarification. Is that right? So that's actually, we need to give the very important note. So in a function, like I said, right, this is considered to be a relationship defined from set A to set B, right? This is the basic definition. However, in order to say this relationship is a function, we have a very important requirement. The requirement is for any element in set A, it must have only one corresponding element in set B. Okay. The function is actually a relationship from set A to set B. We're all on the same page, right? However, in order to make sure this relationship is indeed a function, this is actually a very important requirement. We say for any element in set A, it must have only one corresponding element in set B. There are very important 2 things in this definition. For any given element in set A, it must have only one corresponding element in set B. Looks like they're talking about 2 things. First, number 1, any element in set A, it means that there shouldn't be any exception. Any segment in set A, you should meet such a condition. Condition number 2, there must be only one corresponding element in set B. So let's check it out. at 1, 2, 3, A1, A2, A3, B1, B2, B3, right? This is your set A, this is your set B. The question says what? For any given element in set A, you must have a corresponding element in set B. So A corresponding to B1, A2 corresponding to B2, A3 corresponding to B3, right? Every single element in A must have a corresponding in element B. This is very understandable. Okay, so and this is what? This is exactly our one-to-one mapping, right? Still remember one-to-one mapping? So no problem. This is a perfect candidate for our relationship, right? This is actually a perfect relationship. Any element in A must have one corresponding element in B. Okay, what about the second one? You have one-to-many relationship. Can I meet any element in A must have only one corresponding element in B? You guys do your quick observation. Can you tell me this is yes or this is no? Can you put your answer into the group chat? Can you tell me your answer into the group chat? Everyone, please. Is this a mapping that any element in A must have only one element in B? Everyone, please. This is a one-to-many mapping, right? Can I see any element in A must have only one element in B? Of course not. You see, one element is actually, sometimes they go to A1 and also they go to AB. I mean, they go to like A2, right? So have the A1 parents, A1 father, A1 mother, right? For A2, you have A2 father, you have A2 mother. So one element in A actually facing multiple elements in B. This is not our definition, right? This is not correct. So therefore, the second one, no, this cannot be a function. Because you have any element in A, you're going to go to multiple elements in B. This is not a definition of a function. No. Okay, let's go to our third one. Third one is a multiple to one relationship or many to one relationship, right? You have many guys in A, they will be corresponding to the same guys in B. So my question for you guys is that, can you tell me, is this a function or not? You have multiple elements in A facing to the same element in B. Can you tell me if this is a function or not? Yeah, everyone knows that this is a function, right? Because one element, they're facing to only one element in B. Another element, they're facing to only one element to B. Yeah, it is possible that multiple elements are facing to the same elements in B, right? Multiple elements in A facing to the same elements to B, but it doesn't matter. It doesn't really violate our definition. As long as one element in A mapping to one element B, you're good. This is according to our definition. Okay, so that being said, this is no problem. This is also a definition in function. So that being said, let's try to use our common sense, right? We have this one-to-one relationship, okay? It's kind of a definition for function. We have this many-to-one relationship. These are considered to be a definition of function. However, this one-to-many, this is not correct. So using our kind of a common sense, if I want to ask you to give an example, what kind of functions you have learned so far to respect this one-to-one relationship? 1 equals to kx, right? A linear function. A linear function is exactly such a one-to-one relationship. You give me an x, I give you a y. I give me an x, I give you a y, so on and so forth. There's no ambiguity. Then what about this one-to-many relationship? One-to-many many-to-one relationship, right? What about this many-to-one relationship? Can you give an example for the many-to-one relationship? Of course, y equals to x squared, right? Y equals to x squared is a parabola, right? A parabola, you see, you have two numbers. Let's say -1, +1. And both of them are facing at one value, y equals to 1. So this is like a many-to-one relationship, right? Same thing if you learn like this is the sine x, right? This is the trigonometry, y equals to sine x. Sine x, if I just want to find you what is the value for 0 point, okay? The 0 point, you're going to have what? As long as x equals to k pi, k equals to all those integers, you always have a bound of x that can make sure sine x equals to 0. If you're not so familiar with trigonometry, it doesn't matter. It's outside of scope. I just want to give you a quick example. There are some functions you can have multiple x. All those x can make sure the function value goes to 0, right? I think this is quite understandable. This is quite understandable. Okay, if that's the case, I want to give you another example. Who can tell me if this is a function or not? I have A1, A2, A3, have B1, B2, B3, for instance. I have such a relationship. A1 goes to B1, A2 goes to B2. That's it. I'm going to erase this. Maybe there's not necessary B3. Okay? If I have such a relation, this is set A, this is set B. Okay? I just define such a relationship. A1 to B1, A2 to B2, A3 is just, no one's mapping to it. So can you tell me if this is a function or not? Yeah, I see AB has the answer right away. This is not a function. This is not a function. Why? Everything comes from the definition. Where's the definition? Still have the definition? The definition says, or the requirement says, for any given element in set A, it must have only one corresponding element in B. So this one is good. This one is good. What about this one? This A3 has no correspondence in B, right? You cannot have an element just dangling there without have any corresponding in B. So therefore, this is not a function. Then what about this guy? A1, A2, B1, B2. The relationship is here. A1 goes to B1, A2 goes to B1. However, B2 is dangling there. Who can tell me? Is this a function and not? Is this guy a function or not? Yeah, I see many students, Ben, a lot of students knows that this is a function, no problem. Because according to the definition, every single element in A, they have only one element in B corresponding. But the definition never said, what about B2? I don't really care about B2, right? The question never says this is B2 or not, right? The question only says this A set, every single item in the A set must be mapped to only one item in B set. But for the B, if there are some free items, if there are some dangling items, I don't really care. So far, so good? I think this is a basic definition, right? Yeah, I think all the students, they have the correct answer. That's good. Okay, so I think this is pretty much the second definition of a function, which is quite understandable, right? Before we move forward, I just want to give you guys another quick name, kind of like a terminology. Now we know function is a relationship. Function, let me change to this, is a relationship between set A to set B, right? But this is like a very long sentence, right? In mathematics, we don't like to write a lot of English words. So let me try to use a quick sign to denote such a relationship. So this sentence can be simplified into this: f, comma, a to b. So this is actually means a function defined from a set to b set. Okay, this is more easy way, right? There's more easy way to mark it in such a way. And also, set A is called the domain of function f. Set B is called the range of function f. Again, this is only a definition. It's a terminology. There's nothing too flowery. You just remember it. Because the function is defined as a relationship from A to B. So this set A, we call it the domain of our function. So set B is called a range of our function. That's it. Nothing really flowery. That's the definition. So I'll give an example. Y equals to x. This is our kind of the linear function, right? So linear function, what is the domain? Linear function, if you have the graph, y, x. Linear function goes like this, right? So you can take whatever x, right? This is actually a mapping from a real number to another real number, right? Because x can take whatever value you want to take. So x is pretty much your set A. Y can also take whatever value you want to take. So y is actually your B set. So if I want to ask you what is the domain of function y equals to x, A set is all the real numbers. The domain is R. The range is also R, right? You just basically take whatever number you want to take. Then what about y equals to sine x? If you're not familiar with y equal to sine x, I can give you the graph. Sine x goes like this. So this is always minus positive 1, minus 1. So that being said, it means what? This function is kind of a mapping. Sine x is a mapping from A to B, right? A set A is where the x value can take. The x value, you can take whatever you want to take, right? X value belongs to R. Well, what about the B value? B value is the mapped value because the sine function is actually boundary. It's always between -1 and +1. If you're not familiar, it doesn't matter. We just want to give you this info, this graph like this. So that being said, the range is always between positive, like the -1 and the +1. Okay, -1 and +1. So that being said, the domain is R. The range is from -1 to +1, right? I think this is understandable. Another example, what about y equals to x or 1 over x? This graph goes like this, right? This is your y, this is your x, right? Y equals to 1 over x. So again, what is the, so y equals to 1 over x is defined from A to B. What about A? What x value you can take? X value can take anything except x equals to 0, right? X not equals to 0. Well, we use the word x belongs to R. Well, x is not equal to 0, right? Then what about the y value? Y value, you can take pretty much everything in this axis. So this is basically belongs to R. Is it right? And also, this cannot be 0. Y belongs to R, y cannot be 0. Is it right? Y value, you can take all the values here. You can take all the values here, all the values here. The only thing you cannot take is y equals to 0, right? Because y equals to 0 means x goes to infinity, right? So this is the range of y equals to 1 over x. X can be take whatever the value, but cannot be 0. And because the denominator cannot be 0, right? And what about the y value? One value you can take whatever you want to take. However, you cannot take y equals to 0. Okay, so far, so good? I think this is quite understandable, right? Okay, if all good, so let me maybe give you a sample question. Question number 1. Who can tell me for the following 3 examples, are they considered to be a function or not? The following are functions or not? Number 1, A is positive integers. Oh, I'll say non-negative, excuse me, non-negative. B is real number. I want to define such a relationship from A to B, and my relationship is y equals to 1 over x. Okay, this relationship is a number from A, we do a reciprocal, and then map to B. Second part, A is also non-negative integers. B is what? B is integers. I want to define such a relationship, A to B, y equals to minus 1 to the power of x. Okay. Number 3. I'm going to drag it here. A is what? All the triangles in the plane. B is all the circles in the plane. And my relationship is also A to B. But here I want to be B is the circumcircle of A. Okay. So I'll put it here. A student have a question. I don't really understand what the X and Y have to do with A and B. A and B, A is a set. Okay, that's a very good question. A is a set. B is a set. X is an element within A. Y is an element within B. So if you don't understand, let's come to here. Let's come to here. Okay, any questions, just let me know. This is your A set, right? This is your B set. Well, your A set has a lot of value. Right now, I only give you 2. Your B set also has a lot of value. Now I only give you 2. So what is X? X belongs to A. X can be A1, X can be A2, X can be A3, A whatever. Y belongs to B. Y can be B1, Y can be B2, 1 can be whatever. So A and B, they are considered to be the domain and the range. They are 2 sets. X and Y, they're 2 variables, right? They're 2 elements, right? One is from A, one is from B. So if we want to define a function, let's say y equals to x, right? This is our function, right? We can say the domain is what? A is R, right? You can take whatever real values. The range, B is R, right? B can take whatever values. But domain ranges are 2 sets, right? So therefore, you can say X belongs to R because X is the element. Y belongs to R. Y is also the element. So therefore, that's the relationship. A and B, they're two set. They're the domain, they're the range. X1, XY is your element for X, your element for Y. So this is actually the relationship between A and B, X and Y. Okay? So any question, just let me know. Okay? Yeah, so let's go back to our question number 1. Yeah, give me, like you guys, please post your answer into the group chat. Are the 3 guys, A, number 1, number 2, number 3, are they considered to be functions or considered to be not functions, so on and so forth? Everyone, please, yeah, please participate. Yeah, I see a lot of students have the answer already. Did the other students also try to participate? They are considered to be a function or not? Yeah, everyone, please participate. It's a quick exercise. Okay, I see many students, they have the answer here and there. Okay, so let me try to ask some students, maybe give us some explanation. How do you think of them? They're a function or a not function, so on and so forth. So the first one, maybe we can ask Sophia Tsai to give us some ideas. How do you think for this guy? Yeah, you can unmute yourself. And maybe you can just talk. It's up to you. Hey, Sophia, can you hear us? Okay, so you like to, yeah, that's good. You can actually, you like to talk or you just like to type. It's up to you. There's no, yeah, there's no pressure. In our lecture, it's pretty casual. If you feel a little bit uncomfortable to speak or something, no problem. Okay, cool. Yeah, Sophia basically like typed me the answer. Yes, Sophia said, for this relationship, X is non-negative numbers. Okay, and what about Y? Y is 1 over X. It looks like X, A to B, such a mapping, you can have such a relationship. However, check it out. 0, 1, 2, 3, all the way to whatever, right? Whenever you 1, 2, 3, 4, whatever, whenever you do the mapping, you can find out, what about 0? 0 within X, there's no way for you to put it into the denominator. Is that right? So therefore, it means that all the other values, you can find only one correspondence in B. However, this 0, you can't. You can't find a corresponding for 0. There's nothing mapped in B corresponding to 0. So therefore, this is not a function. Is that right? This is not a function. The second one, okay, all good. The second one, maybe I'm gonna ask Ben Liu, if you would like to talk to some, if you like to talk a little bit. The second one, do you think it's a function or not?
For second one, I think it is a function.
You'd like to give some elaboration? Why it's a function?
Yes, because for example, in here, x can be x. For negative 1 square, 0 square is, I think, is -1. So that is okay, but for the first one, the number cannot be 0. I think number 2 can be a function, but I'm not sure.
Yeah, you're correct. Actually, number 2 is a function. Yeah, that is correct. Just like Ben mentioned, okay, for here, the A set can be 0, 1, 2, 3, 4, 5, whatever, right? And the B can be integers. Okay, I don't know, -2, -1, 0, 1, 2, 3, whatever, right? So using such a relationship, -1 to the power of x, 0 will go to 1, right? -1 to the power of 0 is actually defined as 1. -1 to the power of 1 go to -1. 2 go to 1. 3 go to -1. So that being said, as all those numbers in A set, they would be able to be mapped to the B set. Is that right? And of course, there are a lot of unused items. Let's say -2, -0, 2, 3, 4, but it doesn't matter. Our definition says, I just want to make sure every single element in A must have a correspondent in B. In terms of B, I don't really care. You have something dangling there, nothing dangling there, I don't really care. So the second part is a check. Okay, so far so good. Okay, then what about the last one? The last one is a function or not. Maybe we can ask for Hansen. Hansen Liu, you can give us some quick ideas.
I think so. However, I didn't really learn circumscribe circle that much, but I believe there can only be one for every triangle. So since one A can only correspond to one B, I think it is a function.
Yep, that's the correct answer. Thank you, Hansen. Yes, A is what? A is actually a collection of all the triangles. B is a collection of all the circles. And this A to B relationship makes sure B is the circumcircle of a triangle. Because in our 2D geometry sessions, we have already talked about, as long as you give me a triangle, the triangle can have one and only one circumcircle. Right, this is actually a basic property we learned in our 2D geometry session. Any triangle must be mapped to only one circumcircle. So therefore, you give me a triangle, I would be able to find only one circumcircle. Right? You give me another triangle, I can find another circumcircle, so on and so forth. Okay, so therefore, yeah, this one is correct. This is a mapping. Yeah, of course, there might be some other circles not used, but I don't really care, right? I just want to make sure as long as I have an element in A, I must have an element in B. As a correspondence, voila, my work is done. Okay, so far so good. If that's the case, I want to give you another extension. If exactly the same thing as our question number 3, I'm going to change into this. A is the circles in the plane. B is what? B is the rectangles in the plane. And my relationship from A to B is, or we use X or Y, doesn't matter. And B is the inscribed rectangle. B is the inscribed rectangle of A. Okay, A is a circle, all the circles on the plane. B is all the rectangles on the plane. If my relationship this time is A to B, B is the inscribed rectangle of A. is this going to form a function or not? Yeah, please try to post your answers into the class, into the group chat. Everyone, please. Yeah. So this time we're going to ask Ivan to give us some ideas. Yes or no?
I don't think it's a function because for one circle, you can have many different rectangles. So that would mean it would be one to many, which is not a function.
That is correct. You guys follow Ivan? Because you give me an A, right? This is your A. And you give me a B. B is a inscribed rectangle, right? However, for one given circle, there are infinitely many inscribed rectangles, right? Of course, this is a one-to-many relationship. So therefore, you cannot really see this is a function. Okay? Yeah, I think that's pretty much, I think this is pretty much what I want to say for this easy part, right? Pretty much functions, so on and so forth. I think it's quite understandable, right? Okay, if all good, let's go to one relatively difficult problem. Okay. This problem, let me go to a new page. This problem is actually 2011 Korean Junior Math Olympia practice question. Okay. The question says, given two sets, M is actually X, M is actually what? A collection of the integers from 0 all the way to 11, 1, 2, 3, 4, 5, all the way to 11. And F is actually what? F is A, B, C, D, where A, B, C, D belongs to M. What does it mean? M is a collection, 1, 2, 3, 4, 5, all the way to 11. F is just like a paired set, A, B, C, D. Well, this paired set is not the random numbers. All the numbers must be taken from M. So F can be 1, 2, 3, 4, right? Can be 1, 1, 2, 4, right? Can be 2, 2, 6, 4, whatever, right? As long as the A, B, C, they are collected from M, that's it. I can have my F. I want to define a set. I want to define a map. Let me try to erase this. Define a map function, F, from F all the way to Z. I'm not really mapping from M to F. I'm actually mapping from F to Z, such that A, B, C, D, after my function, it becomes from AB minus CD. Okay? Given U, V, X, Y, if I using this mapping, I goes to 39. U, Y, X, V, given this mapping, I goes to 66. Please determine the value for X, Y, U, V. Okay, so let me try to read the question one more time. Hope you guys understand. I give you two sets. The first set is actually easy. Just basically all the integer numbers from 0 all the way to 11. That is my first set. Why I give you the set? The M is actually used to help you define the second set. The second set, I'm actually give you a collection of all those numbers, A, B, C, D as one pair, A, B, C, D as one pair. But where does A, B, C, D comes from? They are basically taken from M. Like I mentioned here, right? A, B, C, D can be 0, 1, all the way to 11. You just take all the integers to create the pair A, B, C, D. Okay? Now I'm going to define a function. This function is actually from my F set all the way to all the integers. So what does set looks like? From A, B, C, D, I want to times AB together, the minus CD's product. So this is kind of an operation, right? Of course, whenever you have this, you're going to be able to have a number. Okay. So for now, I'm going to give you something. UVXY. After my kind of a function operation, I'm going to go to 39. And I change UYXW because this order matters, right? Because you're going to use the product of first two numbers minus the product of the last two numbers. So if you change the order a little bit, of course, this is going to change, right? From 39 into 66. With all those information, please tell me, what is the value for XY UV? XY UV. So one of the very important part in our lecture, I like to show you guys the thinking process. How do you think as long as you see some relatively difficult problem? And this is not so easy, right? You see, if I'm a little bit drowsy, right? But the thinking process is always very important. We need to see how we're going to think as long as we see such a problem. You have a set M, a set F. F is actually defined using M. And then you have such a relationship from ABCD to a set, to like, to like a whole number, like an integer, right? AB times CD, AB minus CD. And then the question gives you two examples. The question then asks you how to determine this. You know what? All those problems, the thinking process is very understandable. You need to find the breaking point. Whenever you see a relatively difficult problem, how are we going to find the breaking point? So it looks like the only tangible condition you can deal with, you can have some equations, blah, 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 is actually here, right? This is the only condition you can get started because you have some relationship within this. So therefore, let's get started. Let's just try to solve the problem directly from here. Given this relationship, A, B, C, D, they will be mapped to AB minus CD. So we just try to use this. UVXY, this guy will be mapped to what? U times V minus X times Y, right? According to our question, this guy equals to 36, equals to 39. Second, UYXV, this guy is going to be U times Y minus X times V equals to 66, right? I think everyone, we can go to here. Now it looks like I have two equations, but I have four variables, right? It is impossible for me to solve the equation, generally speaking, right? Two equations, four variables, how can I solve it? However, don't forget, the UVXY, are they just random numbers? Or they have some constraint to them? UVXY, are they random numbers? Or there's some constraint to them? If there are random numbers, that's it. I can never solve this equation. There are infinity many solutions, right? Who can tell me where does the UVXY, what is the constraint for UVXY? Who can tell me? Yes, UVXY is here, right? UVXY is defined from F, and all the elements from F must come from M. So UVXY, they are between 0 and 11. And also they are integers, right? Okay. Like I said, if you have this random UVXY, there's no way to solve. But as long as UVXY, they're constrained within 0 and 11, maybe you would be able to solve the problem. Okay. So now let's think about it. You have two equations. And the UVXY, they have some constraint, 0 to 11, so on and so forth. Who can tell me? We have already talked about so many times in our previous lecture. As long as you see two equations, as long as you have no idea what to do, what is the common practice? What is the common approach to get started? This is a very important mathematical thought, right? We talk about so many times in our previous lectures. So for the old students, who can tell me, as long as you have two equations and you're getting stuck, you really have no idea what to do, normally speaking, what is the conditional react you need to do? Who can tell me? We talk about so many times in our previous lectures. Yes, I see somebody has the answer right away. Basically doing some operations, adding them together, subtracting from one to like one from the other, multiple them together, or do some division, right? This is a common practice, or we can say this is a conditional react. As long as you get confused with more equations, do some basic operation, adding, subtracting, multiple. I don't think you want a multiple. This is not easy, right? And division, I don't think you want a division either. So maybe just try to adding them together, subtracting them together, and you might have some idea, right? This is the conditional react. Operation of equations. Okay, try to remember. In our lecture, we're going to give you a bunch of conditional react from time to time, and you can try to use them. If you add them together, you can find out, you can do some quick factorization. You add these two guys together, you're going to have y plus v u minus x equals to 105. If you subtract one from the other, y minus v u plus x equals to 27. There's no magic. You just do this right away. Okay. What are we going to do next? It looks like this guy looks much better, right? And what are we going to do next? This is also a second conditional react. I told you guys already many times before. As long as you see a lot of guys adding them together or multiple them together, normally speaking, I mean, adding them together or subtract them together, normally speaking, this is very difficult because two numbers adding them together equals to 39. There are millions of, there are so many conditions. 1 plus 38, 2 plus 37, all the way, blah, blah, blah. We always like to see from sum to difference. We always like to convert into multiple. Because factorization, you do not have too much flexibilities, right? Two guys multiple them together equals to 105. You do not have too much flexibilities. But two guys adding them together or multiple or like subtracting them together, you're actually doing millions of operations. Is it right? So somebody asked me, what do you mean by operation? Operation means add, subtract, multiple, divide. These are considered to be 4 basic operations. Okay? Okay, somebody will, oh, what does EQ as equations? Equations. Yeah, sometimes I do some acronym. Equations. Okay, yeah, any question, just let me know. You see, I can give you the real-time feedback right away. Okay, so this is the second conditional react I like to talk to you guys. As long as you're dealing with something, adding them together, subtracting, this is not a good thing. Instead, I want to convert it into multiple, because doing some factorization can always, easy my life significantly. Much better compared with dealing with the, adding. So this is the second conditional react. Okay, now it looks like we're gonna do some factorization. Okay, let's focus on the first one. Okay, let's focus on the first one. Y plus V U minus X equals to 105. Don't forget, X, Y, U, V, they from 0 to 11. Okay, so instead of closing my eyes directly doing some factorization, let's try to do some quick range thing. Because U, V, X, Y, they're basic from 0 to 11. So therefore, U minus X, the maximum, it goes to 11. The minimum, it goes to 0, right? U and X, both 11, they goes to 0. One is 11, one is 0, it goes to 11. That's it. So that being said, a guy from 0 all the way to 11 equals to 105. It basically means what? U plus V, they basically, okay, just give me 1 sec. Okay, that's one thing. The other thing, let's check about U plus V plus Y. V plus Y, normally speaking, they should from 0 to 22, right? Because X, Y, U, V, they're from 0 all the way to 11. But you're actually taking something, you're multiple something from 0 all the way to 11, and you have V plus Y is from 0 all the way to 22. If you basically manipulate these two things together, you can find out what? Y plus V can be 105, 11. I just take an integer plus 1 all the way to 22. Is it right? A student has a question. Where does V plus Y and U minus X come from? You don't really understand where this come from? Okay, no problem. A quick explanation. If you want to add these two things together, U times V, give me 1 sec. U times V minus XY plus U times Y minus XV, right? If I want to do this guy, this is going to be U V plus Y minus V X, minus X V plus Y, right? Minus X V plus Y, right? And then you want to do a quick factorization. This is U minus X V plus Y. Is it right? So this is the way how you can get the first one. Factorization. Adding the two things together and do a quick factorization, you get what you have here. Okay, so far so good. Adding them together, doing a quick factorization, you get what you need. Yeah, any questions, just let me know, okay? Okay, so let's continue. So that being said, that's actually the range for V plus Y. Is it right? I think this is quite understandable because U plus V, you have such range 0 to 11, and V plus Y, you have a range 0 to 22. So what is the possible minimum value for V plus Y? As long as this guy goes to 11, you goes to the minimum value of Y plus V. Is it right? So what can you do for minimum value of as long as this guy goes to 11? So we use 105 over 11, because we're talking about integers, right? We want to take a whole number, then plus 1. Sometimes students do not really understand why I need to plus 1. You know what? If you do not understand, forget about this plus 1. You just directly use 105 over 11. Then your range for v plus y will be a little bit wider. Then when you're doing the analysis, you might have some invalid values. No problem. Ignore them. Cross them out. You still know what you're doing. Right? So that being said, you have such a range for y plus v. Okay, y plus v. But don't forget, so that one is actually equals to what? 10 y plus v, 22, right? Okay. You now, this is the range for y plus v. And also y plus v must be divisor of 105, right? Because there must be a factor of 105. 105 is the product of y plus v times u minus x. So therefore, y plus v must be a factor or a divisor of 105. So now you're kind of looking for a divisor of 105 in the range of 0 all the way to 10 all the way to 22. Is that right? So far, so good? So this is the logic, how you can shrink the options for y plus v. Within these two guys, it's very easy to find out, for you to find out what is the value. Actually, y plus v can either equals to 15 or y plus v can equals to 21. Is that right? You would be able to find out only two numbers within this range. And you can make sure these two numbers, they must be a factor of 105. So that actually answers my original question. If you do not really know how to add one, you know, how to get this, not a big deal, because you're gonna get 15 and 21. So you add one, you do not add one, it makes no difference. You guys follow me? Yes or no? Can I have some quick feedback? Yes or no? Because this is not going to make any difference, right? Add 1 plus 1, add 1 minus 1. If you want to just do now, no problem. Because at the end of the day, this is going to be your most constraint. This is going to be a factor of 105. So therefore, you have these two things. All right, as long as you have these things, because v plus y, u minus x, the product is 105. As long as you have this, you'll be able to figure out u minus x. First option equals to 7, right? As long as the upper one is a 15, the lower one will be 7. As long as the v plus y, the upper one is 21, the lower one will be 5, right? This is quite understandable. So that being said, by doing some simple analysis, you actually find out the possible scenarios for v plus y or u minus x. Of course, there are two scenarios, but you see, according to our analysis, you don't really have to do too much logic. You can figure out there are only two possible solutions for these two guys. And similarly, what about the second one? Y minus v u plus x. Y minus v times u plus x equals to what? Equals to 66. Equals to what? 27, excuse me, 27. Exactly the same thing. We can do exactly the same thing as we did here. We want to do some analysis for one guy and using this analysis to determine the value for the other guy. So exactly the same thing. U plus x is between 0 to 22. Y minus v is between 0 to 11. So therefore, what is the maximums you can do, right? Exactly the same thing. U plus x can be lesser than 22, greater than 27 over 11. You take an integer plus 1. Plus, don't forget, u plus x must be divisor of 27. So using these two conditions, you can squeeze out the value for u plus x. It's going to be either equals to 3 or u plus x equals to 9. Exactly the same thing. And the other thing is y minus v equals to 9, y minus v equals to 3, right? Exactly the same thing. A student has a question, why is there a 5 besides u minus, oh yeah, actually this is my typo. Yeah, this is 2, right? 2. Yeah, good catch. Okay. Yeah, because u minus x can have 2 values, right? Either equals to 7 or equals to 5. So therefore you have, so I just want to give you guys a quick denotation. These are the first option. These are the second option, right? So there's basically 2. So this is actually the second one. Okay, this is actually the second one. So now you basically have to see how we're going to deal with that. You want to determine the value for v, for u, for x, for y. Now you already have 4 equations. You can actually make them as one equation, figure out a value for x, for y. You can make this as another possible combination, figure out a value for x, for y. You can make them as a possible combination, figure out an x for value for y, and you can make them as a possible combination, right? To save our time, I don't want to list out them one by one, but generally speaking, you find out there are 4 different combinations. Is that right? Because the upper one talking about, do you guys follow me? Because these guys are talking about the value for y plus x, u minus x. And these guys are talking about the value for y minus v and u plus x. So basically you have 2 sets of equations, and each set contains 2 options. So you have to make the kind of this combination, right? So the black one, the blue one, the yellow one, the green one. So altogether, you have 4 sets of system of equations. And with all of them, you'll be able to solve out all the values for u, v, x, y. You know what? Doing some quick analysis, you can find out actually only one pair is the valid. You can have x equals to 1. I'm going to give you an answer. X equals to 1, y equals to 9, u equals to 8, and v equals to 6. That is actually the correct solution for this problem, right? The other solutions, you might have y equals to -6, which does not make sense, right? Because for our entire solution, x, y, u, and v must be between 0 and 11. Okay, so far, so good. So this problem is a little bit complicated, but think about it. This is also using the basic definition of a function, right? You're kind of define a mapping from a set all the way to a whole number. This is your definition, right? From a set all the way to a whole number. And the $1 million question is, as long as you figure out all those problems, your first reaction is, how are you going to deal with these 2 equations? How are you going to deal with these 2 equations? Are you going to doing some basic operations, adding them together, or like multiple them together, or subtract, so on and so forth? And that's actually the breaking point for this problem. And moving forward, all the way comes to here, you're going to basically do some analysis. 2 numbers, multiple them together equals to 105. You're probably going to do some factorization. And instead of blindly doing some factorization, you can do some quick analysis. Try to shrink the range of these 2 numbers, and taking from there, you will be able to solve the problem. So far, so good? Okay, if all good, let's go to some other problems. Okay, let's go for an AMC problem. Or maybe let's go for Cayley problem first, okay? A Cayley problem, number 2. Okay, this is one of our Canadian problems. We're looking at a problem from 2021. That's the latest and greatest Cayley problem. Cayley, Waterloo Cayley, question number 21. Okay, that's a Waterloo problem. Let's have a quick look. The problem says variables A, B, C, D, E, F, they represent the numbers 4, 12, 15, 27, 31, 39 in some order. Even though I put it in such a way, right, this is exactly the same thing if I want to write into a set. So A, B, C, D, E, F, right? This is one set. I call it maybe F. And I have also a set. Set is 4, 12, 15, all the way to 39, right? And this F, I want to make sure that what? A, B, C, D, E, F belongs to M. Is right? This is exactly the same thing you come from for such a problem. Exactly the same thing. Okay, let's check it out. Okay, in some order, suppose A plus B equals to C. B plus C equals to D. C plus E equals to F. With all those information, what is the value for A plus C plus F? Okay, this is kind of a set as well, right? So you have a collection, 4, 12, all the way 31, 39, whatever, right? Okay, and then you want to create such an ordered pair. The ordered pair, I want to make sure every single item comes from the set, which is exactly the same thing as our previous problem. But now this is kind of a mapping, right? This mapping is not really written, but you have such a mapping. The mapping is kind of A plus B equals to C. B plus C equals to D. C plus E equals to F. It's kind of such a relationship. With all of things, the question asks you to determine what is the value for A plus C plus F. So this is kind of quite similar with the problem we just talked about previously, right? But this guy is more, instead of having all the numbers from 1 to whatever, it just gives you the discrete numbers, 4, 12, 15. So you have such a relationship. Think about it, how we can deal with such a problem. Trust me, most of this set-related problems, they're considered to be easy problems. So you don't really have to do a lot of complicated calculation. Some of the time, very basic strategies can help you solve the problem fairly quick. Instead of going to something super complicated, some basic strategy will help. Think about it. How are we going to deal with such a problem? Yeah, I see Ivan already have some ideas, some big directions. Yeah, I see somebody already has the correct answer. What about the other students? We'll give some time for the other students. Please, everyone, get our hands dirty. Let's try to solve this problem. Yes, I see. Yeah, I see more and more students have the correct answer right away, right? This is a relatively, yes, this is a relatively straightforward problem. So for such a problem, what is the normal strategy? What is the normal strategy? The question gives you a very handful collection, 4, 12, 15, all the way to 39, right? This is not all the way to 39, like 390, right? It's only a handful of numbers. And then the question determines such a relationship. One number plus another number equals to another number. So in such a case, normally speaking, our Canadian exam is actually easy. You don't really have to do a lot of complicated calculation. You can just try to least them out. Or in the more professional term, we use the word enumeration. We can just try to enumerate them out, list them out one by one. We'll see what happens. Within such a range, all those 5, 6 numbers, you can only have 4 plus 27 equals to 31. 12 plus 15 equals to 27. 12 plus 27 equals to 39. That's it. You just basically list out this and there won't be something too crazy. That's it. That's the only possible solution for this problem. And let's check it out. A plus B equals to C. B plus C equals to D. C plus E equals to F. It looks like these 3 expressions is exactly this 3 expression, right? So you only have 3 expressions here and A, B, C, D, right? They're exactly here. But in terms of which one is B, which one is C, which one is A, this is not a magic as well. Check it out. In this expression, you only have 3. You only have C repeat for 3 times. Is that right? And 27, 27, 27. There's only one number repeat for 3 times. Voila. So therefore, C equals to 27. This is a very quick thing, right? You can basically find out. As long as C equals to 27, check it out. A plus B equals to C, right? A plus B equals to C. A plus B equals to 27, right? Equals to 12 plus 15. So my next part is I need to determine which one is A, which one is B. Who can tell me? Which one is A, which one is B? Yeah, everyone knows that B is 12. Why? Because, again, let's check it out. For the original expression, only B happened twice. A just happened once, right? So only you find a 12 happened twice. So therefore, B is 12. This is so easy, right? B is 12. So therefore, A is 15, right? And then when you have all those values, you'll be able to plug in and find out what is value for F, right? So F, I think, is 31, right? Because C plus E equals to F. You can basically solve out all those equations one by one. Then the correct answer, I think this is going to be 73. So this is a super easy problem, right? But from this problem, what I'm trying to say, you can just do some enumeration. List them out. Sometimes when you're dealing with some difficult problem, let's say this Korean Math Olympia problem, you really have to do some analysis, doing the factorization, figure out what's the range, so on and so forth, and then even use different combinations to figure out a value. However, for some easy problem, especially the question already give you a handful of 1, 2, 3, 4, 5, 6. I think there's only 6 numbers. When you have 6 numbers, don't waste your time. Try to just directly list them out and try to find out a pattern. Sometimes the question speaks for itself, right? You really do not have to do a lot of hardcore calculation and you would be able to get pretty much all the information you need. All right, let's do a quick summary what we have learned so far. today, this is the first lecture. This is the basic of our function. We don't really talk about too many important things of function. We basically talk about the definition, right? What a function is, how to define a function from a human word's perspective, from a set's perspective. And during that process, we actually spent some time ask you guys how to define a set, right? How to define a function between these two sets. There are some criteria. One of the most important criteria is as long as a function is defined from A to B, I want to make sure every single element in set A must have only one correspondent in set B. And this is actually the mapping relationship. As long as you know this, you'll be able to know the basic idea how to define a function. And taking from there, we actually give you guys some quick questions, how to use our definition, right? Some easy problems, some relatively difficult problem. Some easy problem you can just directly use in the enumeration. Some relatively difficult problem, you need to do some manipulation and then find out a relationship, right? And then doing some enumeration thereafter. But generally speaking, this is a quick start for our function. We understand the basic definition. And from next lecture, we're going to go to some real properties of a function. Some increasing, decreasing, some kind of function graph, so on and so forth. And we'll be able to give you more real problems from Canadian and American exams and some national, international math Olympia as well, try to help you guys to utilize the technology to solve the real problems. Okay. So after today's lecture, I'm going to upload our assignment into our Google Classroom. So you'll be able to access the Google Classroom and you see the assignment. You have 1 week to finish the assignment. As long as you're done, try to re-upload your solution, your answers into the Google assignment, like the Google Classroom. I will be able to mark your assignment. So the next lecture, I'm going to be asking some student to give us a quick presentation for your homework. And trust me, as long as I ask you means you do a good job. So I won't be making you like a fool. So no problem. So don't be shy. Just feel free to give us a presentation showing us how to do the homework, and then we'll take it from there. All right, that's pretty much for today's lecture. You have any questions for me? All good? Yeah, you can always talk to me offline using WeChat or email, so on and so forth, and I'll be able to help you guys out. All right, that's pretty much for today's lecture. I hope you guys enjoy the rest of the weekend, and I'll see you guys for the next week. Bye, guys.